But sometimes the probabilities of a certain statement, uh, you may give some lower limit and upper limit. Of course, the lower limit will be always 0 and upper limit will be 1, but still there can be improvement on these probabilities. So there is a Chevyshev's inequality which gives you the lower bound and upper bound. If you may, lower bound and upper bound of the probabilities of a certain statement. So let us look at what exactly I want to convey the message for the Chevyshev's inequality. Say, suppose x is normal, mu sigma square, and if I want to calculate what is the probability x minus mu less than 2 sigma, so basically it is x lies between mu minus 2 sigma, mu plus 2 sigma, and we know that this probability is 0.95, which is the exact value. But if we use the Chevyshev's inequality, the condition is that you require only the mean and variance. Okay, first two moment. So in that case, I'm just calculating the value using the Chevyshev's inequality, which is x minus mu less than k sigma is greater or equal to 1 minus k square. So here k is 2. Okay, so x minus mu less than 2 sigma will be greater than equal to 1 minus 1 by 2 square, since k is 2 here. So if you look at this value, so it is 1 minus 1 by 4, which is 0.75. So what this statement tells you, it tells you that probability x lies between mu minus 2 sigma and mu plus 2 sigma will be at least 0.75. So instead of telling that its value will be between 0 and 1, you are telling that its value will be at least 0.75, means it will be between 0.75 to 1. So here you do not require the form of the density function. Okay. So if you know the form of the density function, then of course the exact value can be calculated, and as you have seen here, it is coming 0.95. So 0.95 the exact value, whereas here we are giving you the lower bound, that the value of this probability that x lies between mu minus 2 sigma, mu plus 3 sigma is 0.75. So to apply the Chevyshev's inequality, we need only the mean, knowledge of mean and variance. Similarly, if you look at x minus mu less than 3 sigma, then the exact value is 0.99. Whereas if I use the Chevyshev's inequality, so it will be 1 minus k is 3. So 1 minus 1 by 3 square, which is 0.899. So 0.89 and 0.99 if you compare, so we are closer to the exact value. Of course, as I told you, that if you know the density function, the exact values can be calculated, and it is 0.99. But many applications you may not have the knowledge of the form of the distribution, then still some observation you can make about the x minus mu less than 3 sigma, which is 0.8. So at many places, these Chevyshev's inequalities are used, and in proving various theoretical results also we use Chevyshev's inequality. So another problem I'm just trying to explain you. Let x be a random variable which mean is 3 and the second moment is 13. Instead of variance, the second moment about the about 0, that is raw moment, is given, that mu2 dash. So it is 13. Find the probability lower bound of this x lies between minus 2 to 8. So basically you have to convert this into the standard form. So x minus mu by x minus mu. So what we do, we subtract minus 2, minus 3, x minus 3, 8 minus 3. So it becomes minus 5, x minus 3 less than 5. So it is equivalent to the standard form x minus 3 less than 5. Okay, so x minus 3 less than 5 will be at least. Now you have to find out the value of k from here. So k sigma is 5. Here you see this 5. You have to extract what is the value of k here. So k sigma is 5. Now sigma is known because the second moment is known. So sigma square will be 30 minus 3 square, which is 4. So sigma is 2. So it is 2 k, 2k is equal to 5. Okay, k sigma is 5. So sigma is 2. So 2k is 5. So k equal to 5 by 2. So here I can use this 1 minus 1 by 5 by 2 whole square, which is equal to 1 minus 4 by 25, and it is 0.84. So this is how do we use that. Now take another example. Is it fine? So take another example. Suppose we are tossing a coin and xi that I get tossed. If head comes, we assign 1, and if tail comes, assign 0. So we have tossed n times. So when you toss n times, that you get the number of heads. Okay, because if you sum, then you will be summing 1, 2, 1, 0, 1, etc. So number of heads in n tosses. And here, if we take the proportion, so xn bar is the average number of heads you will obtain when you toss the coin n times. So if we give you a statement, if the probability that the average, okay, average number of heads which we have defined here lies between minus 4.4 to 0.6 is at least 0.7. If the average number of heads lies between 0.4 and 0.6 is at least 0.7, then what should be the value of n? What should be the value of n means how many tosses we have to make in order to satisfy that xn bar, the probability of xn bar lies between 0.4 to 0.6 is at least 0.7. So here, even if we know the distribution, we can use the Chebyshev inequality, because finding the distribution of xn bar is not an easy task. So what we do using the Chebyshev inequality, we need the mean of xn bar and variance of xn bar. How to find the mean of xn bar and variance of xn bar? We know the distribution of xi. Xi takes 1 and 0 with probability half and half. So expected value of xi will be 1 into half, 0 into half. So it is half. What will be the expected value of xi square? 1 square into half, 0 square into half. So it is half. So variance of xi is expected value of xi square minus expected value of xi whole square. So 1 by 2 minus half whole square. So it is 1 by 4. Now, what will be the expected value of xn bar? Because the variable, random variable here under consideration is xn bar. So now we have to know the expected value of xn bar. So expected value of xn bar you can calculate, because 1 by n summation of expected value of xi. So it will come half. Okay. And variance of xn bar will come same way you calculate 1 by 4n. Otherwise, also I have given you the result that distribution of x, whenever you have to deal with the sample, whenever you have to deal with x bar, so in that case mean will be always mu, variance will be sigma square by n. Okay, so here mean is half and variance will be sigma square by n. So sigma square is here, if you see, it is 1 by 4 and divided by n, so 1 by 4n. So if you remember the standard result, you can find out directly mean and variance. Otherwise, you work out here. So standard deviation is 1 by 2 root n. So now we can write, see, xn bar, we go back to the statement. So probability that xn bar lies between 0.4 to 0.6. So I will subtract mean of xn bar from here. So it is 0.05. So xn bar minus 0.5 and minus 0.5 is subtracted both the sides. Okay, because here we are trying to put into the standard form of the Chebyshev inequality. Okay. Standard form is probability that x bar minus mu is less than k sigma. So that's why I have subtracted the mean here. Okay. So this is xn bar minus 0.5 less than 0.1. This we can write xn bar minus 0.5 less than 0.5. So this is, if you convert this, because here you see, we were asked to find what is the probability that xn bar lies between 0.4 to 0.6. So this statement is equivalent to this same, the first statement, that the question which we were asked to find out here. So if you simplify uh, this, so we have just converted into the standard form. Okay, so this is 0.1. Okay, now so k sigma is 0.1 here. K sigma is 0.1. So sigma we have already calculated, 1 by 2 root n equal to 0.1. So k we will get 0.2 root n. So according to Chebyshev's inequality, we apply this 1 minus 1 by k square. So k square will become 0.04 n. Just we have substituted the value of k here. So 1 minus 1 by 0.04 n should be greater than equal to 0.7. So if you simplify this expression, you will get n should be greater than 83. Means that you have to toss at least 83 times in order to have the probability that xn bar lies between 0.4 and 0.6. So this is another application of this Chebyshev's inequalities. So Chebyshev's inequalities are used only when we need to find the lower bound or upper bound, and only the mean and variances of the random variables are known, or sometimes when it becomes difficult to derive the distribution of a particular random variable. So there are 4 forms. Basically, if you remember one form, it is sufficient. What I discussed is this one, the A. X bar minus mu less than k sigma equal will be at least 1 minus 1 by k. So this is one form. Another form, if you write the complement of this, so it will be 1 by k square, means it gives you upper bound since it is less than equal to 1 by k square. Sometimes this sigma is adjusted, so it is also written as probability x minus mu less than k will be 1 minus sigma square by k square. Okay, and the complement of this. So these are the various forms of the central limit theorem, but you don't have to remember all the form. One form is good enough. So if you remember this one, the first one, it is good enough. Okay. So this is what about the Chebyshev's inequality. So now if you have any question, I can answer. Otherwise, we move to the next topic. We want to somehow finish today. Is it fine? Hello.
Sir,
Yes, sir.
हाँ बोलो.
so you said regarding the doubt, you said that you'll tell us in the class.
Yes, doubt in the assignment.
Yeah, you said that you will discuss in the class.
Yeah.
One question was
So
there.
actually, one student sent me the doubts, and I responded to him. Okay.
Yes, sir, it's me only.
Yes. I today I sent you the mail.
Yes, sir. In
Yeah.
question number 56, you said that you will discuss in the class. So will you do it now or later?
56 was what about? Let me see. 40, yeah, 56 was there or 57 was there?
So 56.
Yes. 56 I am going to teach in the class today.
Oh, okay, sir.
Okay. Yes. 56 I am going to teach you. And the second problem basically you is a tricky problem, that geometric progression. Okay.
Yes, sir. The question was that what do you mean by fractions here? I didn't understand.
Thanks. Fractions means the common ratio could be in the form of the fractions also. It could be say in the form of um, what
Yes, sir. I've included it by multiplying by
three,
like.
3 by 2, 5 by 2, 7 by 2, something like that. And because once you consider 3 by 2, then you will get some numbers.
Okay,
Say
sir. Yes, sir.
4, 6, 9 you will get. If you consider 5 by 2, then 4, 10, 25 you will get. 7 by 2, if you consider 4, 14, 49, you. So like this, we have to consider the fractions also, I think.
Okay. Okay, sir. I'll see it again then.
Yeah, you see it. I still am looking at that, trying to count. But first part, it seems to be okay, 53 by that when integer part you have considered.
Oh,
So
yes, sir. Yes.
anyway, I'll write the complete solution and we'll see. So now we are going to consider discuss the another topic, which is the function of the random variable basically. So let me share this. These are again all small topics, but sometimes they are very useful. Yes. So can you see it now? Is it visible now?
Yes, sir.
Yes. Yeah. Okay. So this topic is function of the random variable. Uh, so what happens many times that if we know the PMF or PDF of the random variable X, we need to find the PDF and PDF or PMF, whatever it would be, of some function of the random variable X. So function could be x squared, 2x plus 1, mod x, x by 2, or it could be any other function also. So the problem is knowing the PDF or PMF of random variable x, how to find the PDF or PMF of the random variable y. So here we are considering, uh, let x be a random variable. As I told you that it could be discrete and continuous, so I use this slash discrete and continuous. If it is discrete, then we have a PMF, otherwise PDF. So Pxx, Fx is no. So certainly x is a random variable, we know its probability, mass function, or density function. Now, if y is equal to gx is some function of the random variable x, okay, then the problem is how to find the PDF or PMF of random variable y. So as I told you, this function could be say 2x plus 3, dx equal to sine x, dx equal to x square, any sort of function we can consider. So the problems we can discuss in two ways. One is that by considering the discrete random variable, things are a little simpler. So here I am just considering one example through which you can see that how to find the PMF of y. So x is a discrete random variable. We need to find out the PMF of random variable y. So the first step of this is that since the PMF is given, means you know the range of x is possible values of the random variable x will take. So knowing the possible values of random variable x, knowing the function, I can find the possible values of the random variable y. And since we know the PMF of x, correspondingly we can map and we can find the probability of random variable, PMF of random variable y. So let us take a very simple example. So suppose we toss 3 coins and we know the probability mass function, which is x is the number of heads. So 0, 1, 2, 3, and these values corresponding to the value, these represent the probability. Now suppose we need to find what is the PMF of random variable y is equal to 2x minus 1. So this is a function, which is a function of the random variable x. So as I told you, first thing is that you know the range of x, you can find the range of y. So corresponding x equal to 0, if random variable x takes value 0, the y will be minus 1. X takes value 1, y will be 2 minus 1, 1. X equal to 2, so 4 minus 1, 3. X equal to 3, so 6 minus 1, 5. So what we do now, in the first column, first we write here that what is the values taken by the random variable y. So random variable y takes value now minus 1, 1, 3, and 5. So having done this, the second column we write the what is the probability mass function, so of y. So probability mass function say y takes minus 1. Now y takes minus 1 is equivalent to probability x equal to 0, because here if you see y equal to minus 1 means we have got y equal to minus 1 when x was 0. So what is probability of x equal to 0? We go back to the PMF of random variable x, and from here it is 1 by 8. Similarly, y equal to 1, it is 3 by 8, because y equal to 1 you get when x equal to 1, 3 by 8. Y equal to 3 we have got when x was 2, so it is 3 by 8. And y equal to 5, x equal to 3, it is 1 by 8. So for it, if you sum this, it is 1. It's a valid probability mass function. Now second example, if you take, suppose I change the functions. My function is now y equal to mod x minus 2. So given the PMF here of random variable x, we need to find the PMF y, which is mod x minus 2. So what will be the corresponding value? So when x equal to 0, y will take 2. When x equal to 1, y will take 1, because x equal to 1, it is minus 1 and mod value, so 1. X equal to 2, it takes 0. X equal to 3, it takes 1. Y. So corresponding value of y we can write first. So y takes value 0, 1, and 2. So y equal to y, the first row on the top, we write, and corresponding value we have written 0, 1, 2. Now the next step is to what we have to find probability of y equal to 0, probability of y equal to 1, and probability of y equal to 2. So if you see here, probability of y equal to 0 we have got from here, and it comes when x takes value 2. So probability x equal to 2 is 3 by 8. So 3 by 8 we have written. Okay. Now when y1, y takes value 1. Now y takes value 1 when x is 1. Rx is 3. So x is 1, Rx is 3. So plus, so 3 by 8, 1 by 8, 4 by 8. Y equal to 2 comes when x equal to 0. So it is 1 by 8. So what we have got now? We have got the probability mass function of the random variable y, which is 0, 1, 2, and correspondingly we have mentioned the respective probability. So check is that is sum should be 1 and these values, none of the values should be negative. So this is how we find the probability mass function of y given the probability mass function of the random variable x and its EMF. Now, let us move to the continuous case. So now what we are considering that x is a continuous random variable and its PDF is known, which we represent by small fx, and we need to find the PDF of y equal to gx, which is some function of the random variable x. So our job is to find what is the PDF of y. So that's why fyy, as I told you in the beginning, that this random variables are used to represent the subscript in f, lower subscript, to represent that you are dealing with that particular random variable. So here we are dealing with random variable x, here we are dealing with random variable y. So we need to find what is the probability density function of the random variable y. So usual procedure is that before I give you the direct formula, I will just explain you that steps usually involved in finding the CDF is CDF of y. Finding the PDF of y is to first obtain the CDF, then differentiate with respect to y. You will get PDF, and then find the corresponding range. So first step is find the CDF of y, then find the PDF of y by differentiating, and then range of y. So let us take an example to explain this concept. Say suppose fx is equal to x by 8 and it is 0 to 4 and 0 otherwise. Our function is given y is equal to 2x plus 8. So we know the PDF of random variable x. We have defined the function which is 2x plus 8. Now we need to find what is the PDF of y. So as I told you that we can first find the CDF of this random variable. So CDF of this random variable is fyy. Fyy is nothing but probability y is less than. Just write the definition of the random variable. CDF definition of random variable. Once you have written this, substitute y. So y is equal to 2x plus 8. So 2x plus 8 less than y. So x, simplify this. So x will be less or equal to y minus 8 by 2. So what is this? This represents the CDF of random variable x. Okay. So CDF of random variable x, we have written fx, that capital Fx, and is in place of small x, it is y minus 8 by 2. So it is y minus 8 by 2. You can put this some other variable, say x dash, and then fx x dash, and then you substitute x dash. It is the same thing. So now you are all familiar with this concept. So you can directly write this is the random variable x, and this is the value. So fx y minus 8. So now I know the CDF of the random variable y. So differentiate this with respect to y. So this side we can write, when we differentiate, it becomes the density function. Okay. And this side, if you differentiate fx dash y minus 8 by 2 and differentiation of the this factor y minus 8 by 2 with respect to y, which gives you 1 by 2. So this is fx, because when you take the derivative of the CDF of x, it becomes the density function with inside that bracket y minus 8 by 2 into half. Now this we know, because if you look at that, in the beginning you are given density function of x is x by 8. So in place of x we substitute y minus 8 by 2. Okay, because now this small x has changed. Okay, so y minus 8 by 2 divided by 8 into half already there. So this, if you simplify, y minus 8 by 30. Now what will be the range? Corresponding range of x is 0 to 4. So when equal, you substitute here small x, it is a function. So when x equal to 0, it is 8, and when x equal to 4, it is 32. So y will take value between 8 to 16. Sorry, here it is 4. So x equal to 0, it is 8, and when x equal to 4, so it is 4 into 2, 8 plus 8, 60. So it is 8 to 60 and 0 otherwise. So in order that you can easily check that in this range the function is non-negative, and if you integrate 8 to 16, y minus 8 by 30 divided by 32, it will 1. So it's a valid PDF, and this is how do we get the PDF of random variable y, knowing that PDF of random variable x. Take another example. Here you will see something different. Suppose in general we are considering a random variable x and its density function is known fx. Okay. So we need to find what is the density function of random variable y is equal to x square. Okay, remember that y is equal to x square graph is of this form. So it is decreasing function, then it is an increasing function. Okay. So later on we will state one more result. So here, but as I told you the procedure, that you write the CDF of y. So CDF of y is less than equal to y. That is the definition of random variable y. Now, since y equal to x square, so I will write x square less than y. So if I simplify this, x will be minus root y to plus root y. Now we know the result of CDF. X lies between a and b, so it will be fb minus fa. So fx root y minus fx minus root y. Okay, remember that this subscript plays very important role, so don't forget to write, otherwise you will get something different. And here it is fyy. So see that so here you say that when you differentiate, now we have to differentiate with respect to y. Okay, so when we differentiate this with respect to y, it will become fy dash y. That is the, when you differentiate, it will become basically this is okay. Now when you differentiate this, we have to differentiate with respect to y. So fx dash root y, and you are differentiating root y, so it will be 1 by 2 root y. Similarly, the second factor you are differentiating, so it will be fx dash minus root y. Okay, and differentiation of this with respect to y, so minus 1 by 2 root y. So if I simplify this, all this will become the density function of y. This will become the density function of x, but inside the bracket it will be root y. Okay, 1 by 2 root y plus this minus get multiplied, so plus derivative this density function of x, but it will be in place of a small x, it will be minus root y, and 1 by 2 root y. So 1 by 2 root y fx root y plus fx minus root. So it is basically sum of the uh, two parts. Okay, and region you will see that why it is happening, that I will state the theorem. So, but even if you do not remember the theorem, this procedure is a standard procedure. Okay, so say for example, suppose I say x follows normal 0. There we derive the result for any density function. Now we are saying that suppose x equal to x follows normal 0, 1. What is the density function of y equal to x square? So since x follows normal distribution, so we know it's standard normal means mean 0 and variance 1. So fx will be 1 by root 2 pi e to the power minus half x square. So now in order to find the density function of y, we will just substitute 1 by 2 root y. Here it is clumsy, but anyway you can see here 1 by 2 fx minus fx root y. So in place of x you put root y, so it will be y. So 1 by root 2 pi e to the power y by minus y by 2, and this side also minus root y whole square, so it will be again y by 2. So if you combine the complete result, means 1 by 2 root y, and this will be twice of 1 by root 2 pi e to the power minus y by 2. So 2 get cancelled, so 1 by root 2 pi y to the power minus half e to the power minus y by 2. So this is nothing but density function of gamma half n. How it is gamma half n? If you see, gamma density function is lambda to the power r, gamma r, x to the power r minus 1, e to the power minus lambda x. Okay. If you substitute lambda half, gamma half, so it is this form. So x to the power minus half, e to the power minus n. This matches here. Okay. 2 to the power half root pi. Okay. So basically it is a standard result that when x follows normal 0, 1, y equal to x square follows gamma half and half. And once we know it is gamma half and half, I can directly calculate mean and variance of random variable y instead of going through the long derivation that using expected value of y equal to y times fy dy and then integrating. So such type of result helps uh, helps us to quickly find out the mean and variance, because once you have found out the uh, standard form of which resembles with some of the known distributions, say in this case it is gamma, so we can easily calculate this. So finally, a result has been stated in the form of the theorem for easy use. This result is derived from
Sir, it should be 2, right?
it should be
2, the last one.
हाँ लास्ट में 2 होगा, ये करेक्ट कर लेना, ये ना 4/2 ये 2 होगा. So so the whole things have been stated in the form of the theorem. Only thing is that this particular result which I am going to state is true only when the function is monotone function. It is either increasing or decreasing. Okay, and when the function is both increasing and decreasing, then we have another result. So first it says that if x is a continuous random variable with PD of fx and y is equal to gx is a continuous function of the random variable x and g is monotone, so it is either increasing or decreasing, then the density function of y can be written as fx g inverse y and the absolute value of dx over dy, dg inverse y dy or dx over dy, where x is g inverse y. So the proof of this result is simple. Say, suppose, as I told you, right, what is the CDF of y? So y is less than y. Y equal to gx is known. Okay. So in place of y, I substituted g of x, which is less than y. If g is an increasing function, so it will be x less than g inverse y, we can write. Once we have written this form, then fyy equal to fx, because this is the CDF of x, g inverse y. Take the derivative. So when you take the derivative with respect to y, it will become the density of y, and this becomes the density of x, and the derivative of g inverse y with respect to y. I think here it is y. Here it is y. It is d. Okay. So ultimately it becomes dx over dy. So this is the result when x is g is an increasing function. Now if it is a decreasing function, then same way y is less than y, gx is less than y. Now if it is a decreasing function, then it will be x greater than g inverse y. Okay, because here we are saying that it is a decreasing function, so equality will change, inequality will change. So this we can still convert into the standard form, that 1 minus probability x, that complementary function, 1 minus probability x less than g inverse y. Now again you take the derivative. So when you take the derivative, the first part is 0. This is this density function, and the derivative of this part. So this is written like this. So ultimately, if you combine both the result, then we have, when g is increasing, g is decreasing. So in order to write both the result into a combined form, so we can use the mod value, and then it is dx over dy. Okay. So this result we can directly use to derive the density function. This result we can directly use to derive the density function of the random variable y, if the function is known to us. So same example I will explain you. Here the steps is that uh, y is equal to 2x plus 8, the function is known, you solve for x. Okay. So when we solve for x, it is y minus 8 by 2. So this is my g inverse y. Take the derivative with respect to y, dx over dy. Take the absolute value, it is half. So as per the formula, fyy fx, y minus x equal to g inverse, here g inverse y. So g inverse y is uh, y minus x equal to g inverse y. So y minus 8 by 2 into half. So you get the same result. So this particular result, you can remember this one. Sorry. Okay. So this is the main result which is used to calculate the density function of random variable y, knowing the density function of x. Now there is a advanced result. What happens if the transformation is not one to one? Okay, in that say it is partly increasing, then partly decreasing. Say y equal to x square, you have seen. So here what we do, this is the range space, okay, of the density function. This can be decomposed into a finite number of disjoint set. Okay, this total range you divide into the decompose into disjoint sets, which we call it chi1, chi2, chi-m. This is the capital chi, chi, which is used to denote the symbol in various references. So here just to write that it has been, the total range, it has been decomposed into disjoint so that in particular ranges it has one-to-one transformation. So y is equal to dx defines one-to-one transformation of each chi I in the domain D. Then the density function of y is equal to gx can be written as summation. So summation I is equal to, you have decomposed into m parts, so I is equal to 1 to m fx gi inverse y and absolute value. That same result we have written, where x is equal to gi inverse y denotes the inverse of y equal to gx in the when x belongs to chi. Okay, so this particular result we can use when you have a function where partly it is monotonic, increasing or decreasing, uh, again increasing, decreasing. So say for example, y is equal to mod x, you can decompose into two parts. One is minus infinity to 0, 0 to infinity. And so in this case, you use the first result, which we have derived, which we have stated in the form of the theorem before. And similarly, in this range, you use the same result and then combine, because you have decomposed into two parts, so it will be fx minus y and it will derivative, it will be 1. So this is how it is. Is it clear? Hello?
Yes, sir.
Okay. So now there are a few more things are there. So maybe tomorrow class I will cover quickly. Sometimes we need to find minimum and maximum. And the last thing is that another important result that uh, here, if we consider G as a capital F, that CDF, that 56 problem which has been given in the assignment sheet, that if we know the density function of random variable x or CDF of random variable x, then what is the distribution of y is equal to capital Fx, where f represents the CDF. Okay, so function f, instead of g we are taking capital F, which is the CDF. Okay, so we will show you that it follows the uniform distribution. So in the next class we will discuss this. So again, these are the small things which are left over, and maybe after finishing we will start the joint distributions. Means we have to discuss the function distribution of more than one random variable. So what is the theory, and then in particular we shall discuss the bivariate normal distribution. Okay, so we will stop at this point. It is fine.